Okay, so I'm starting with the third part of chapter 16. So let's see how far this will go. With the third part of chapter 16, what I'm doing now is talking about judging the acidity of an acid according to the pH value. So for this section right here, we're jumping right into it and saying that the pH, remember the pH scale I talked about before this? The pH scale that goes from 0 to right before 7, right? And then you have after 7 all the way to 14. So right at 7, that pH is neutral. A pH that's less than 7 to 0, or less than 7 in general, that pH is acidic. Then a pH that's above 7 is basic. So from above 7 all the way to 14, or what we call above 7 is basic. Right at 7, that is neutral. And then below 7 is acidic. But exactly how do we get those pH values? The pH values, by the way, are never negative. How do we calculate the pH value? In the solution, when the hydronium ion is released by an acid, that hydronium ion, the negative log of that hydronium ion gives you the pH value, a positive value that we can use to judge the acidity of the acid. With that being the case, the higher the hydronium ion, there's an inverse relationship. The higher the hydronium ion, the lower. This results in a lower pH. Okay? So we have an inverse relationship here. When the hydronium ion is large, the pH value is small. That is why we say a pH that's less than 7 is actually an acid. And so moving on from here, we're told here a pH that's less than 7 is acidic, pH larger than 7 is basic, pH equals to 7 is neutral. So you want to make sure you have this formula written down as we go through formulas. I mean, I'm covering everything you need to know, but this formula has to be written down somewhere as you're summarizing your notes to study for your homework and the exam. You want to make sure you write this formula down somewhere. And as we move along right here, to figure out the hydronium ion from the pH, you want to use this value right here. Now, I mentioned this to the class that the way I try to remember this and rearranging logarithmic equations, pH equal negative log base 10 of hydronium ion concentration. Okay. Then I also mentioned this before because I'm kind of talking about this after I've taught the lesson. So I've had some feedback from students on a better way to communicate this. I mentioned this to the class that when I was learning this way back when, many eons ago, I noticed a trend in the lesson that every time P was used before a value like pH, essentially the P stood for negative log to the base 10 of whatever symbol came after the P. Now, this made more sense when back at home we were using H plus to communicate the level of acidity, right? Or the acidic ion. So what I mean by that was back at home we use hydrogen ion or the proton to communicate the acidity. So if you had the proton and you're trying to figure out the pH, you essentially took the negative log to the base 10 of the hydrogen ion. And negative log base 10 stood for the P part of the pH. That way, later on, when we have OH minus and we take the negative log base 10 of OH, we get P of OH. You see how this works out? Anyway, that was something that I noticed. As I said, there's a trend in chemistry as we're learning trends of different things. There are patterns and there are rhythms in chemistry. So once we recognize this here, the base is 10, right? Now, looking at this relationship here and trying to derive the formula for the hydronium ion, there's a 10 power hydronium ion concentration right here. So what I did when I was learning this, in learning to flip this around, I rewrote the 10, but this time it was power pH, and then brought in the negative, and that was equal to H3O plus. Of course, you can just memorize it, but I told you guys my mind doesn't work that way. I have the kind of mind where I don't just look at this and remember it. I have to somehow derive it. I can derive stuff. I just have to be able to connect what I know to what I'm trying to get to. And that's what I'm showing you right now, how I connect it, because I don't have the kind of mind that is able to retain abstract, disconnected information. I do better when the information is connected and it's a sequence somehow, like the backstory, stories, period. Anyway, moving on. So from here we have two formulas. The formula where we get the pH value from the hydronium ion concentration, and then the inverse of that where we get the hydronium ion concentration from the pH value. Now we're moving on. So they're telling you, what exactly does the pH let you know? What does it imply? What's the implication? Why should we care? Okay. They want you to know that when you're seeing something and you're measuring the pH of a solution and the number you're getting for the pH is lower, that's telling you the solution you're looking at is acidic, is more acidic. That means you have more hydronium ion than you do hydroxide. Okay? This is outweighing the hydroxide. But when you have a higher pH, that means that you have more hydroxide. The dominant species in that solution is more hydroxide. This information is important in the next chapter, chapter 17, when we're dealing with salts, right? That part is very important. Okay, I'm going to keep going because the mic is responding to my sound, to my voice. Okay, so from here, let's actually do some practice problems. This one here, where it says find the pH or OH minus. So what I'm going to do here, since I already told you guys about the POH and I was told by my student she prefers the POH route, I'm going to bring that in right now. So we learned that you can have a pH which is equal to negative log base 10, right? This is the default log on your calculator of H3O plus or H plus. And then there's such a thing as POH equal negative log base 10 of OH minus. Because I was told by my students, the feedback I got was that this route is a lot easier. I'm going to bring this early on in the lesson because when we look at everything overall, this path will be easier. So I'm going to show you here that pH plus POH equal 14. I know we covered this later on, but guys, I have been given feedback by my students when I trust them to say that this route is a lot easier than what we're doing before. And in the past, I've had students struggle here, so I'm going to try this different approach. Okay? That, once again, if you have the H3O plus, plug it in this formula to get the pH. If you're given the OH minus, plug it in this formula to get the OH. From the POH, you can get the pH. So we're going to be solving it that way. Okay. Okay, so we are reintroducing the formula for pH. pH is equal to negative log base 10 of H plus, or pH is equal to negative log base 10 of H3O plus. As I mentioned before, it makes more sense that the P stands for negative log base 10 of what comes after the P, right? So in this case, it's H, and H here represents H plus. But the H plus can be written as H3O plus because when the hydrogen ion gets in the water, it actually combines with the water to form hydronium ion. Okay, now that I've finished that part, remember we have two formulas to work with. Even though the book goes with KW, I got feedback from my students that the POH version works a lot better. So I'm going to bring in POH here is equal to negative log base 10 of the OH minus concentration. pH is equal to negative log base 10 of H3O plus concentration. And for that reason, pH plus POH is equal to 14. Having these three formulas right here will really help you as you navigate through solving for pH using the H3O plus and the OH minus. Okay. Once again, my students told me as they were reviewing for the exam, this formula is a lot more friendly than the KW formula. Remember, you also have KW is equal to H3O plus times OH minus. And you can use that to solve for, if you're given H3O plus, you can figure out OH minus, knowing what KW is. But I was told this is not as friendly as this one here. Y'all just like whole numbers, okay? This is essentially when you take the negative log of this number here, or sorry, not the number, but the formula, you get this. So this is actually derived from that. Anyway, moving on. Let me go ahead and use these three formulas to solve the problem they're asking for. The first one is asking you to find the pH of each solution at 25 degrees. and we're told here we're given H3O plus, we can plug that into the pH formula. pH equal negative log base 10 of H3O plus, right? Once you have the concentration. pH is equal to negative log base 10 of 1.8 times 10 power negative 4. I need to write this correctly. And therefore, pH is equal to, let's see how that works out. Where's negative log? I put the negative here, my calculated log, and then 1.8 exponent negative 4. Yeah, I messed up earlier and I had to re-record it. So I get 3.74. Then they say indicate whether the solution is acidic or basic. So the first one has a pH is equal to 3.74. I would say this is acidic. Whoa, sorry, I dropped my calculator. Okay, this is acidic. The next one. For our next one, we're going to be working on pH given OH ions. So in this case, you cannot plug the OH directly into the pH formula, right? So what I'm going to do here, let me go ahead and erase this. I need this space. I'm going to write a little bit big and be comfortable. But I'm going to be using those formulas here. This is for, we said it was acidic, right? So I can plug the OH directly into the POH formula. So I'm going to do negative log base 10 of the OH minus. I do have the OH minus concentration right here, so I'm going to use negative log base 10 of 1.3 times 10 power negative 2. And this gives me what? Let me see if I can plug this number in here. Can I plug this? Okay, this won't work. From scratch, negative log, the base 10 is implied, 1.3 exponent negative 2, close parentheses, equal. Okay, so I end up with 1.886 for my POH. But remember, they want the pH of each solution. So I have to get the pH from the POH. Well, I remember that pH plus POH equal 14. Therefore, pH is 14 minus POH. So that would be 14 minus 1.8 to give me 12.11. So this is going to be basic. Yeah, basic. Okay? So remember, the first one was acidic, the second one was basic. If you have any questions, feel free to email me. So they work it out here. They get acidic for the first one. I don't know why I have a blank space. I guess it's a break for your eyes. Second one ends up being basic. So I've pretty much followed along before, but I was told once again, this process here is a lot more lengthy, and I guess it's all that scientific notation, and y'all prefer whole numbers over these, but feel free to use this formula because it does work too. In this problem here, we're solving for the H3O plus concentration, the hydronium ion concentration from the pH. So the formula here is to get the hydronium ion concentration from the pH, take 10 power negative pH, and you get that value. So pH is given to us here as 4.8, so 10 power negative 4.80. You want to multiply that out or plug in your calculator. That should work out. So it's going to be 10. Where's the hat? Can I see a hat here? Power negative 4.80. And your answer ends up being 1.585 times 10 power negative 5. So the power here is very similar to this number right here. Okay? But yeah, that should be your answer. What they have here? Well, they round it up. 1.6 times 10 power negative 5 molar. Okay? So this should be pretty straightforward. Let's go ahead and move on. See, I have a lot of blank pages here. So, ooh, that's 2 blank pages. Okay. I kind of already gave you guys this formula right here. As I mentioned before, this formula is actually birthed from, I don't know where this came from. It's birthed from the relationship between H3O plus OH minus, when you multiply these two, you get KW. Okay? So if you take the negative log of everything here, you end up with negative log base 10 of H3O plus, negative log base 10 of OH minus, negative log base 10 of KW. KW is equal to 1.0 times 10 power negative 14. Okay? So essentially here you end up getting pH plus POH equal PKW, where PKW is the same thing as 14. And so you want to have this equation here in your list of equations, your summary, your note cards. I'm assuming you're keeping those as you take your homework and prepare for, well, as you work on your homework and take the exam. Okay? So moving on over here, we're seeing a summary of the 6 strong acids mentioned again. This time it's 6 strong acids. We're told that of the 6 strong acids, 5 of them are monoprotic. Monoprotic refers to the number of hydrogen ions that are ionizable in the acids. So mono is saying that in those acids, only one proton can be ionized. Okay? There's only one proton, or only one proton is ionizable. And then diprotic implies that 2 hydrogen ions can be ionized. So 2 protons or 2 hydrogen ions. So diprotic is H2SO4. Once again, both hydrogen ions can be separated from the molecule because the OH bond is weak. Okay? So what has monoprotic or diprotic acid got to do with acidity? I'm going to use this example here to illustrate, but I won't use this part here. I want to draw an ice table. I want to be comfortable. So this is kind of a short version of the ice table. I want to use the full ice table and be comfortable because I feel like that's being more cohesive, right? So I'll start with 0.1 molar amount of HCl versus zero point 0.1 molar amounts of H2SO4. So trying to figure out which is more acidic. We have the same concentration but different acids based on the pH. So I'm going to take my HCl aqueous, react this with water, liquid, and then since it's a strong acid, I have to use a one-way arrow. And then with acids, you're always making H3O plus, because this is an acid, it has to correspond with this. And so the H3O plus means the hydrogen is going over here. What we have left behind is Cl minus, aqueous. Okay, let me remove this from here so it's all clear. Okay, we're going to use the ice table to figure out how much H3O plus is generated when the HCl interacts with the water, when it gets dissolved in water, because acidity is all about the amount of H3O plus. Okay, so I'm going to use the ice table and it will tell me how much we have. Now, this is a strong acid, like I mentioned before, so it's going to be a one-way reaction, not a equilibrium. But I'm still using the ice table. Remember, in this case, this is going to be the end because one-way reactions have ends, while two-way reactions or reversible reactions have equilibrium. Anyway, I'm starting with 0.1 molar of the acid. We can ignore the water part because, once again, water doesn't get involved in the equilibrium. In this case, doesn't get involved. So we'll ignore that part. In the beginning, before ionization happens, we have 0 amounts of hydronium ion, 0 amounts of chloride ion. Since we're looking at a strong acid, we're looking at 100% ionization, right? Like we mentioned before. So that means all of the available concentration of HCl gets used up or gets processed, right, in the ionization. So all of this gets processed because it's 100% ionized. And then in the process, you're making, because you have a 1 2 1 2 1 2 1 stoichiometry, you're making 0.1 molar. 0.1 molar. Okay? When you add To get the amount at the end, you want to add these two, you get zero, meaning that once you take the strong acid, put it in water, you should not have any more acid left in the molecular form. All your molecular form should be ionized. So all you have is the ionized form, H3O plus and Cl minus. So here we should have zero point 0.1 molar, zero point 0.1 molar. Now we used this table before. Doesn't this look familiar? We were trying to communicate back there that HCl is a strong acid because the amount you start off with of the molecular acid matches the amount of the hydronium ion produced. Well, to figure out the pH here, you do negative log base 10 of H3O plus, and that essentially gives you, oh, hold on, negative log base 10 of, what do we have here? Zero point 0.1. Wait, log 0.1. This gives you 1. Okay, so the pH is 1. So when you have zero point 0.1 molar HCl, essentially the hydronium ion produced because it's a strong acid is 100% same amount. So the pH is equal to 1. Okay, conclusion, strong. Okay, now how does this compare to H2SO4? Remember, this is monoprotic, right? Meaning for every one formula of the acid that gets processed and gets ionized, we make one amount of the hydronium ion. It's a 1 to 1 more ratio because you only have one hydrogen ion. Let's see how this plays out with sulfuric acid. In the case of sulfuric acid, you have two ionizable protons, right? H2SO4. This is aqueous. Again, you add this to water, you get liquid, still one way arrow. Even though technically, okay, technically the second hydrogen gets removed in an equilibrium, we won't complicate things right now. This is a strong acid, so we will assume it's 100% ionized. That's what SA stands for. Then we're going to be getting what? H3O plus aqueous plus SO4, 2 minus. Let's keep going. Once again, this is going to be zero point 0.1 molar to begin with. This is initial change, equilibrium. Moving on, let's see what happens here. Cancel this whole part here. Okay, initial is 0, initial is 0. Moving on from here, once again, this is, oh, I just realized something. My equation is not balanced. Bad teacher. That's me, y'all. That's me, my bad. This is not balanced. I need to double this here. I need to double this here. So for every one amount of sulfuric acid that gets processed, two amounts of water are needed to really take in both hydrogens. And then we get twice the amount of hydronium ions and then sulfate. Okay? So that's very important on the change part because that's where stoichiometry comes in. So this is a strong acid, right? That means all of this gets processed in one cycle. But when this gets processed, our mole ratio is 1 to 2 to 2 to 1. That means the amount that gets processed here, you need to double that here. It's going to be zero point 0.2 molar. And then same amount back here, plus zero point 0.1 molar. And then, of course, go ahead and add these to get the amount at the end. This plus this becomes 0. When sulfuric acid is ionized, once again in water, you will have no molecular sulfuric acid left over. All you will have is zero point 0.2 molar uh, hydronium ion, had a brain freeze, and then zero point 0.1 molar sulfate. So in other words, you have twice the amount of hydronium ion from the sulfuric acid. Okay? The end. Now, how does this affect the pH? Well, the pH is always measuring the amounts that you have in the end or at equilibrium of the hydronium ion. So this time we have negative log base 10 of zero point 0.2, and this will be, let me see what we got here. Log base 10 of zero point 0.2, and we end up with negative log base 10, right? Points, it's 0.698, well, zero point 0.7. Our pH is 0.7. Ooh. So now we're comparing H2SO4 with HCl. Remember, the pH scale goes from 0 to 7, 7 to 14. When you get closer to 0, this tends to be the most acidic. With that being the case, this is more acidic than HCl, why HCl has a pH of 1, while H2SO4 has a pH of zero point 0.7. So you can once again use the pH to judge the acidity of an acid. In this case, monoprotic versus diprotic. Oh, by the way, while we're here, I couldn't resist. While we are here, please look at this, right? Remember, for every one molecule or one amount of HCl that ionizes, we get one positive charge particle and one negative charge particle. So this is saying this. If you were to draw a mental model, I couldn't resist, okay? We'll get to this in lab. When you have HCl in here, for every one I'm going to draw three HCl particles. For every one positive ion that's produced, it shows right here, for every one HCl that gets processed, you make one amount of H3O plus and one amount of Cl minus. In the mental model, we tend to not draw the water. Oh, I'm just realizing the connection. We don't draw the water. Okay? So we draw one H3O plus for every one Cl minus. One H3O plus for every one Cl minus. One H3O plus for every one Cl minus. Okay? So I said that's going to draw three, so that's what it looks like. So this means I just added three amounts of HCl. If I do the same, but I add three amounts of H2SO4, do I have room? Okay, I make my container big or long. If I had three amounts of H2SO4, whoa, I can do this. For every amount of H2SO4, I'm making twice the amount of H3O. So I have to write here H3O plus. If I have three of these, I'm going to make six, right? H3O plus, H3O plus, H3O plus, H3O plus, H3O plus. I should make six if I have three beginning molecules, right? It should be twice the amount. But if I have three beginning molecules of H2SO4, whatever amount I have for the H2SO4, I should make the same amount in the SO42 minus, right? So SO42 minus 1, SO42 minus 2, SO42 minus 3. But 1, 2, 3, 4, 5, 6. Yep, the end. Okay, that's how it compares. You have twice the amount of H3O plus, and that the implication of that is you have a much lower pH. It's more acidic because you have twice the amount of acid ion. Okay, moving on. I did mention percent ionization, right? And we said that for a strong acid, you have 100. The number that goes here is going to be 100%. Okay, and I said this over and over again using the ice table that if it's 100%, that just means the number you have, okay, the number you have down here should match the number you have up here, or in this case, it would be double, right? For strong acids, you see right here, this will kind of match that, right? I think this is a better picture of strong acid versus that one, even though this is a strong acid too. When it's a weak acid, we mentioned earlier, the amount of the H3O plus at equilibrium is lower than the amount you started off with. Okay, so of course we're going to be using the ice table over here, so I'm going to move on. Let's see, my pencil is glitching. Let's go straight into this. So for right here, we're going to start with finding the H3O plus concentration of a weak acid solution. Okay, in these kind of questions, we're trying to find the H3O plus. By default, what you're looking for is the amount at equilibrium. Okay, for this one here, this is your initial amount, and they have to give you a Ka. So there's a Ka missing here. So let me go find my Ka. I don't know why they left it out. It has to be somewhere here. Oh, 4.9 times 10 power negative 10. Okay, hold on a second. Okay, so Ka, I'll write it here. Ka is 4.9 times 10 power negative 10. Okay, when you're writing out your acid equilibrium, we're working with a weak acid. Okay, remember weak acid, you have to have your equilibrium here because it's a Bronsted-Lowry relationship. And then you want to have weak acid goes with Ka. This is almost like a package deal. For the weak acid that we give you the formula, what's implied in there is that you have to write your equilibrium. So the equilibrium shows how the H3O ion gets formed, and then of course you do have your Ka. So it's a combo. Weak acid formula is given to you, you write your equilibrium, but you also need your equilibrium to go with your Ka. So my weak acid given to me here is HCN. And of course, they have to give you the concentration, right? zero point 0.1 molar. Okay. So I'm going to have HCN. That's my weak acid. You write your equation. The weak acid is added to water. It's always added to the water in this section here. You have your equilibrium arrows. It forms H3O plus. Okay, plus what's left over here, Cn minus, the conjugate base. Okay, so remember, Ka, the equilibrium constant for the acid, the A there stands for acid, is because we have a weak acid given to us. Okay, from here you will draw your ice table. Probably should have made this a little bit smaller. Let me see if I can make this a little smaller. Maybe not. Hold on, give me just a second. Oh, that works. Okay, so we have initial change equilibrium. They gave us an initial amount of zero point 0.1 molar, and then I can just block this whole section out. This will not be involved. Then we have this part right here. And let's see, where am I? Where do I go from here? Initial amount of the hydronium ion formed is 0. Initial amount of a cyanide ion is 0. Cyanate. Cyanide. I don't remember how to pronounce this right now. Okay, Cn minus. This is 0, right? And then let's see the amount that reacts in terms of, since we don't have the amount that is present at equilibrium, the amounts here or here, we can't kind of reverse engineer our way into getting this number here. So for right now, we'll use a placeholder letter until we solve for it. We will say that if X amount of HCN reacts, that means X amount of H3O plus is formed because we have a 1 to 1 to 1 ratio plus X, right? Go ahead and add the initial and change to get the equilibrium amount. So we have zero point 0.1 minus X. We got X here, we got X here. Okay, these are placeholders. Once we solve for X, we'll come back, plug it in here, and then figure out what is what. Okay, now we're going to write our Ka expression. You want to not skip this step. Your Ka expression shows your products of the product ions. These are your products here and here. Raised to the power of the coefficient. The coefficients here are 1 and 1, so it's implied, so we don't really have to do anything else apart from that. Divided by the aqueous reactants, the concentration of the aqueous reactants. Concentration of HCN, and ta-da. Plug in your values, right? For your Ka expression, the numbers you're plugging in there are the values you have, either the numbers or the variables you have in terms of X at the equilibrium level. So what I'm trying to say is you plug in these into that. Okay. Ka is over here. 4.9 times 10 power negative 10 equal X times X, because that's what these are at equilibrium, divided by zero point 0.1 minus X. Okay, if we don't do anything with this equation here, we're going to find ourselves with a quadratic equation, and we don't want to have that. So to make our lives easier, we're going to use the 5% rule. The 5% rule is essentially saying that if you take your Ka and divide by the initial concentration of your acid and you multiply this by 100, as long as you get a number that's less than 5%, as long as the number here is less than 5%, you can go ahead and delete or approximate that minus x to 0. Only this one here gets approximated, not this, because if you make that 0, it will mess up your equation, then you cannot solve for x, right? So only this x here gets approximated to 0. Doesn't that make your math a lot easier? Yes, it does. Okay. Oh, I already approximated without really checking. My bad, y'all. This is the reason why I did this. I could do it just because my Ka value is power negative 10. Okay. When you do a bunch of these, you see how it plays out. 4.9 times 10 power negative 10. If your Ka value is at least power negative 5 or smaller, you can go ahead and assume it will pass. Divided by zero point 0.1 times 100. Let's see how that plays out. So we got 4.9 exponent negative 9 equal divided by zero point 0.1 times 100. We get 4.9 times 10 power negative 6. This number is really, really small. It's smaller than 5, right? So if your number has the power of negative 5, most of the time you can assume this is negative 5. You can assume that the 5% rule will be fulfilled, or it will pass the 5% rule. Maybe we should call it the rule of less than 5%, right? The goal is to get a percentage that's less than 5% to allow you to approximate this. Okay, let's keep going. So now our math is x squared. I consolidated this part here over zero point 0.1, and this part is 4.9 times 10 power negative 10. So I'm going to cross multiply here. This here, I get x squared equal this and this, I get 0 0.1 times 4.9 times 10 power negative 10. I end up with 4.9 times 10 power negative 11 x squared. So what is x? X is equal to 4.1 exponent negative 11, right? I need to find the square root of that. So square root of 4.9 times 10 power negative 11. Okay, where is the square root of my calculator? It's kind of dark. Is the light on in here? Oh my goodness. I think this is it, right? Square root of my answer. Okay, so I'm getting 7.6 times 10 power negative 6. So I go back in here. Remember, this is a placeholder. Erase that, erase that, erase that, erase that, erase that. Minus 7.6 times 10 power negative 6. 7.6 times 10 power negative 6. Oh no, this is, okay, I'm sorry. Now I'm rushing through this. Plus, oops. As I said it, I'm rushing even more. Okay, hold on a second. Let me collect myself. This needs to go because this doesn't belong here yet. I have to actually work that out. Plus 7.6 times 10 power negative 6. Plus 7.6 times 10 power negative 6. So this becomes 7.6 times 10 power negative 6. 7.6 times 10 power negative 6. When you subtract this and you round it up, you get 0.1. Okay? What we need here, though, to find our pH, that's what we're looking for, right? Did they say find your pH? Oh, no, they just asked for the H3O+. plus. Is that all they were asking for? Because here they say the pH. Okay, if they're asking for just the H3O+, plus, that value is 7.6 times 10 power negative 6. If they want the pH, though, I'm going to go ahead and find the pH while we're here. pH negative log base 10 of this number, 7.6 times 10 power negative 6. So I'll take the log of my answer and I should get my pH. 5.15 if they ask for the pH. If all they're asking for is the H3O plus that's formed at equilibrium, then your answer will be 7.6 times 10 power negative 6 molar. And this will be your answer. Okay, let's see what they asked for. I think they were just asking for H3O plus. Yeah, that's it right here. They were just asking you to solve for H3O plus. I was just going above and beyond. They never asked for all that. Okay. Okay. So I mentioned this earlier. You have this table right here. And remember, if the Ka values are less than 1, then these are weak acid. This is weak, weak, weak. And you have these organic acids. Look at that. Oh my goodness. This is weak. And then the smaller, sorry, the larger the exponent, when it's a larger, like -5, -6, -7, that means the acid is very, very weak. And that's why we can actually approximate out the X when we're solving for the H3O plus concentration. Okay, so I'm going to skip over this part. This is a verification of our answer. They said pH was not asked for in this problem. It's like they heard me or they saw me do what I was doing. Okay, let me continue from here. Oh, this is that one problem. This is, yeah. Okay. We're working on this right now. I think I can handle this tonight. Let me see what time it is right now. Okay. I think I can do this tonight. Okay. So let's go ahead and solve for, we'll find the pH, like it says right here, find the pH of a weak acid solution in cases where the X is small. Wait, no, this is wrong. Oh, where the X is small, approximation does not work. No, they should have said where the X approximation does not work. I don't know what they're trying to say here. Where the 5% rule fails. Okay. So let me show you up front how the 5% rule is failing. You take your Ka, divide by your concentration of your acid times 100. 0.011 divided by zero point 0.1 times 100. 0.011 divided by zero point 0.1 times 100. What do we get? 11%. This is larger than 5%. So yeah, they're right. The small approximation of the 5% rule fails. So I'm going to write here 5% rule fails because we got more than 5%. 11 is definitely bigger than 5. What does that mean for our future? That means that when we're writing out our ice table, we cannot approximate the X out. We have to use all the variables in solving for our problem. Okay, let me get to it. Our acid here is HClO2, right? HClO2. And the amount we have here was zero point 0.1. That's the initial amount, ICE. And of course, this is aqueous. This is added to water. Water is liquid. We have our equilibrium arrow here. We got H3O plus, aqueous. What's left over after you remove the H here is ClO2 minus, aqueous. Oh, do I even have enough room for this? And I can do this. Let me make this slightly smaller. I don't know why I write so big, then I have to decrease the size. Just a little bit. Just a little bit. Okay. So Ka here is, where is it? 0.011. Man, I barely fitted that in there. Okay, let me zoom in. Now I feel a lot better. I can do that. Okay, 0.011. So let me work this out. We're starting in the beginning. Once again, we have our ice table here. Excuse my horrible line. These lines are not straight, y'all. I don't want to try to make them perfect. These are fine. Okay. Okay, so hold on a second. This is really bothering me now. I said I wasn't going to make them perfect, but now it's bothering me because I just have too many parts down here. I should just be okay with this. Y'all, it's a struggle. Okay, this is a little better. Okay, and this is here, and this is here. Okay, this looks more like it. Okay, so we're ignoring this column right here. Initial amounts of H3O plus and ClO2 are 0. And then let's start. The change will be in terms of X, right? Remember, the amount of reactants are decreasing because they're reacting. We don't know how much is reacting, so for right now, X is the placeholder until we solve for X. Plus X, plus X. Where am I getting these X's from? X is the placeholder. Reactant amount decreases with time, so minus X is reacting from here, this initial amount. This Product amount increases with time. Stoichiometry is 1, 2, 1, 2, 1, 2, 1. So it's going to be minus x plus x because products are being made, reactants are being used, correct? Then go ahead and add these two. 0.1 minus x at equilibrium, x, x. Then we're going to be dealing with the Ka expression that says H3O plus, this is going to be your product, that one here, times concentration of ClO2 minus, that's that product, divided by this reactant, HClO2. Remember, we ignore the water. Water does not make it into the Ka expression. Then plug in your values. You take this number that goes over here, 0.011 equal x, this is x, right, divided by 0.1 minus x. We know ahead of time that this doesn't pass the 5% rule. We already checked that. So just move on. Just move on. You can do this. I believe in you. When I say you, I mean me. I'm trying to encourage myself. I'm like, you can do it. It's kind of late at night, but you can do it. It's not that late. Okay, moving on. So what I'm going to try to do is solve this part first, right? Remember, I multiply these out and I get x squared. So essentially I have, okay, I'll try to go step by step and not skip too many steps. X squared, this is going to be over 1. And then here I have 0.1 minus x, right? So multiply this here and multiply that there. I get x squared equal 0.011 0.1 minus x. Okay? I'm going to distribute this. So multiply this into here, multiply that into there, and we end up with 0.0011, right? I want to make sure I copy the number correctly because I struggle with transcribing correctly. So now I have 0.001 minus 0.0011, right? Minus 0.011x. This is x squared. Now bring all these numbers over. Remember, when these numbers cross over the equal sign, the sign before the number changes. So this becomes negative. This will also cross over and this will become positive. So this becomes x squared. And I'm going to write this equation so it can fit the quadratic equation form. X squared. This moves over first and becomes positive 0.011x. And then this moves over last and this becomes negative because it's positive here, right? So negative 0.0011. This equation now fits the quadratic form. Now in the quadratic equation, x is equal to negative b plus or minus square root of b squared minus 4ac over 2a. I think. Let me verify that. Because I'm like, I said that too quickly. Does that look right? Let's see. I have to verify it, y'all. Yeah, they take a while. So where are they? This is them testing it. Negative b plus or minus 4ac 2. Is it 2a? Do I have 2a here? I think I have 2a. Yep. Okay. So to kind of show you what I'm going to be doing next, I'm going to be selecting what is a. A is the coefficient that goes over here, so that's going to be that. And then that's also going to be A. And then I'm going to use different colors to highlight these. B is going to be this, right? And then C, let's use another bright color. We want to use orange. Let's try orange. This is C. Okay, so it's going to go over here. Okay, let's go ahead and plug these numbers in and solve for our unknown, which is x. Okay, so x is going to be equal to negative 0.011 plus or minus square root of 0.011 squared minus 4 times, this is 1 implied, right? 1 times negative 0.0011. That goes over here. Over 2 times 1. So I'm trying to use the colors to keep track of what I'm doing, plus to make it kind of colorful and fun while we're doing all this math, right? Okay, I want to take this step by step. I'm going to just copy this part here. Negative 0.011 plus or minus. I want to go ahead and work on this part here. And then I'm going to work on this part here and then kind of put it all together. I know all of this is going to be over 2, right? So square root of 0.011 squared is equal to, this is going to be 1.21 times 10 power negative 4. So this part here is done. The next part will be this whole part here. I'm going to be working on that part. So that's going to be, so clear this out, negative 4 times 1, yeah, I did that, times negative 0.0011, close parentheses. This is, no, no. Okay, 0.0011, come on, 11, okay. Something went wrong here. So this is supposed to be, oh, this is supposed to be minus. That's what I did. Let me try it over again. Negative 4 times negative 0.0011, close parentheses. Okay, now it works out. And I end up with a positive 4.4 times 10 power negative 3. Okay, so we're adding these two numbers to each other. 1.21 exponent negative 4, close parentheses. I end up with negative 0.011 plus or minus 4.521 times 10 power negative 3. Oh, the square root is here. Oops. Square root is here over 2. Okay? So while I'm here, I'm going to resolve this part, get the square root of that so I can have a number. Square root of that, square root of my answer. This gives me plus or minus 0.0672, negative 0.011 over 2. Okay, so this is where you split this into two parts, right? So one part is going to be negative 0.011 positive or plus 0.0672 over 2, or the other one. This is one possible value of x. The other possible value of x is going to be negative 0.011 minus the bottom, going the bottom route this way, 0.0672 over 2. We're close to the end. Very close. Okay, let's see. For the first one, I'm going to take this one here and then take negative 0.011 plus 0.0672 divided by 2, and you get 0.028. That's x. Okay, so here's the thing, right? When you work on a bunch of these, you recognize a trend. If one of the x's is a positive number, the other one is most likely a negative number, and that one's probably the wrong one. But I'm going to work it out since I want to show you how it works out in the end. Okay? Negative 0.011 minus 0.0672, we get negative. You cannot have a negative concentration. Divide by 2. Oh, divide by 2. Negative 0.0391. So this is impossible. So the answer has to be this for x, right? So go back here. What was it again? 0. I already forgot. 0.028. So you go back here, erase this. 0.028. 0.028, 0.028, 0.028, 0.028, 0.028, 0.1 minus 0.028, 0.072. Okay? But they asked you for pH. I know it's been a long time ago. So pH is equal to negative log base 10. All they care about is this. 0.028. So take negative log, so negative log base 10, 0.028, close parentheses, and we get pH is equal to 1.55. The end. I know it's like, what a long question. It wasn't really that bad. I hope this was correct though, because as I said, it's kind of late. Let's see what they said. They started from here, went on to here. Did the 5% rule, said it failed. Oh yay, look at that. Solve for X, went back, plugged it in, and then they found the pH. So we are correct, and we're moving on. That was a big one. Oh, this is different. This one here is different. Most of our lab stems from a question like this. So when we're working on this one here, we'll be doing a lab very similar to this. Okay. In this problem here, it says find the equilibrium constant Ka when pH is known. So we're starting from pH and then filling the ice table to solve for Ka. Okay, in this case, once again, we have a weak acid, the general one, Ha, and we have the molarity of the weak acid, 0.1 molar, and then we have the pH, 4.25, and we're asked to find the Ka of this generic acid. Okay, so they want you to know, or they want you to figure out what the Ka is, given the weak acid Ha. So I'm going to write my equilibrium equation plus H2O liquid. You have your equilibrium arrows here, H3O plus A minus. Okay. And you were given initial concentration. You have initial, you have change, you have equilibrium. Let me complete this table. Hold on a second. I'm really trying with these lines. Oh, it's a struggle, y'all. Okay. There. A little better. Okay. What was the initial amount again? 0.1. 0.10 molar. And they gave us the pH. Was it 4.25? 4.25. Okay. We know how this goes, right? This here, we're not going to use that. Initial amount of this is 0, 0 because nothing has happened yet. And then for right now, our placeholder is going to be X. Based on stoichiometry, X of this reacts is 1, 2, 1, 2, 1, 2, 1. So that means X is going to form here, X is going to form here. This is going to be X, this is going to be X, this is going to be 0.1 minus X. Okay, now, when we work on this in the lab, you will see that the pH meter, the probe, it's a little stick looking thing. It's not really stick, but it's a probe. When you put in the solution, the probe is calibrated to recognize only this ion, the ions H3O plus that's released in solution. So the pH probe is only measuring what's here. Okay. So from the pH, we can find H3O plus, which we said earlier is equal to the 10 power negative pH. So that will be 10 power negative 4.25, which is H3O plus is equal to, I want to do my own math, right? To give you guys a chance to work with me. 10 power, where is the power? Power negative 4.25. This is equal to 5.62 times 10 power negative 5. Once again, kind of close to that. Okay, so essentially what we are finding here from the pH meter is the equilibrium amount of H3O plus, which is the same thing as this number right here, right? It's essentially this, this is this. So now that we found this, we're going to put this back in here. 5.62 times 10 power negative 5. We are following a pattern here, sort of. Okay. I don't know why I did this. Okay, I'm trying to erase right now. This is a struggle. 5.62 times 10 power negative 5. 5.62 times 10 power negative 5. This is minus, right? This is plus. 5.62 times 10 power negative 5. 5.62 times 10 power negative 5, right? Because we're adding this here. So 0.1 minus our answer ends up rounding up to 0.1, because even for the unknown fake acid, 5% rule rules. It makes, right? It passes. Okay, let me continue. I'm getting delirious now. Oh, they asked for the Ka. So Ka is equal to, once again, the amount of H3O plus at equilibrium times the amount of A minus at equilibrium. So the products first, you multiply those divided by HA, the reactant. Remember, do not include water because water does not make it into the equilibrium equation. Okay, so we have these numbers at equilibrium. Ka is equal to 5.62 times 10 power negative 5 times 5.62 times 10 power negative 5 divided by 0.1. Okay, can I go back? Open parentheses, 5.62 exponent negative 5, close parentheses, square that, divided by 0.1. Can we do that really? Delete. I get a Ka that's equal to 3.16 times 10 power negative 8. Then I didn't really check my math. What is it? Ka equals 3.2 times 10 power negative 8. I kind of did it all in one with my math. Let's see if that works out over here. Do we get 3.2 times 10 power negative 8? Yeah, they wanted it differently, but we got it. So we're making progress. I'm very happy with that. Okay, give me just a moment. Let me go ahead and look at this and see what I want to do next. Because I think I want to do, okay, I think I might start the last video with the base part. Yeah. So I'm trying to categorize this so in such a way that it kind of makes sense. Oh, I just shared a video. Okay. I can do that one last. Okay, I can do this. Let me go ahead because I don't want the video to be too long. So I think I'm going to do the last part with the salt later. Okay, so once we got done with that part, we have one more part to work on, which is percent ionization, right? We're done with this part here. Percent ionization. With percent ionization, you want to take the hydronium ion that actually got ionized at equilibrium, or the end, divided by the initial amount of the acid, like we saw before, times 100. If these numbers are the same, you get 100% ionization. Okay, so in this case here, that we want to see how much of the hydronium ion gets formed. So they gave us a Ka for the acid. Our Ka is 4.6 times 10 power negative 4. And then here we have HNO2 aqueous plus H2O liquid to give us H3O plus aqueous plus NO2 minus aqueous. Okay? So we are asked to find the percent ionization given 2.5 molar nitrous acid. So 2.5 molar is the initial amount of this. Let's see if we can find the change and the equilibrium amounts. Okay, so once again, ignore this part. This is going to be 0, 0 in terms of x, minus x because it's a 1 to 1 to 1 mole ratio, plus x, we get x here, we get x here, we get 2.5 minus x. Okay, now we want to, our goal here is to find this part here, just in case. Notice that most of the time we're trying to solve for H3O plus, either to solve for it by itself to get the pH, or now to get the percent ionization. Okay, we're always trying to look for H3O plus because this whole chapter is about either H3O plus or OH minus. Okay. Ka, work on your equilibrium expression, is H3O plus this product times the other product, NO2 minus, divided by this HNO2 concentration. We want the equilibrium amounts, right? So before I continue, I want to see if the 5% rule passes. So once again, say 4.6 times 10 power negative 4 divided by 2.5. We're not very sure with this one, so we'll check. Do we get a percent that's less than 5%? 4.6 exponent negative 4 divided by 2.5 times 100. Oh, it's a little high, but it's not greater than 5%. So this passes because it's less than 5%. Passes. Great. That was a close one. So we can say minus x here. That was a close one, right? Minus x here to simplify our math. Okay. Plugging in the numbers, we have 4.6 times 10 power negative 4 equal x. I plugged in these two numbers, divided by the bottom number, 2.5. So much easier math, right? Multiply this. So I'm going to do this part here first. I get x squared equal 2.5 times 4.6 times 10 power negative 4. Okay. 2.5 times, open parentheses, 4.6. Where's the exponent? Exponent negative 4, close parentheses. I get x squared equal 1.15 times 10 power negative 3. Okay. X equal the square root of 1.15 times 10 power negative 3. This is 10. So where's the square root of that? Square root of my answer equal. So x is equal to 0.0339 molar. Okay, they wanted the percent. So when I go back here and I plug this in here, oh, I ruined it. I'll put it back. 0.039. Oh, there's two threes. Hold on. 39, right? Plus, I need more room than that. Plus 0.0339. 0.0339. 0.0339 minus 0.0339. So plus, right? So 2.5 minus our answer is equal to 2.466. Okay, so these are the molarities of the reactants and products in equilibrium. But now they want a percent ionization, right? So what we want once again is this number here. We're doing something with this number and comparing it with this number here. So you're going to take the amount of H3O plus formed at equilibrium over the acid that we started off with, right, times 100. So that's going to be 0.0339 divided by 2.5 times 100. So, of course, once again, this is a weak acid. Why? This number does not match that number right there. So 0.0339 divided by 2.5 times 100 is 1.356% or 1.4%. Man, that's a weak acid. Only 1.4% of it ionized. Very weak. Okay, so this is 1.4% of the original amount. And that's what I was doing earlier in the previous video. Whenever I did the 0.07 or whatever, I was trying to get a 7% ionization. Just in case you were wondering. Look, 1.4%. Okay.